In this video, I'm going to go over the basic outputs from a thermal analysis or human comfort simulation in Climate Studio. You remember in the last video, we ran a very simple model, single zone. We had picked a template from our library, talked about that a little bit. And it was the residential multifamily housing. We said it didn't matter which one we picked. And we went over all of these inputs that are in that template. Again, these are the same inputs in all the templates. It's just these that we went over the settings and explained what they meant. So now let's look at the outputs, what we're learning from this simple analysis. So we go to our results tab here, and I ran this. Well, I named our model from the last video carefully, and this is important. You really do. Once we get into a daylighting analysis in Climate Studio, we won't really need to do this as much, though we still should. Here we really need to clearly name our simulation so that we understand what it is that we simulated. If we don't do that, we can't tell the difference later. I mean, you can come down and export a report. It's a big CSV file. It's not that well organized. Well, it's just there's a lot of information there, and so it's kind of clunky. We can also make our own spreadsheet to keep track of things, but especially in these simple models, just make sure you're naming things as clearly as you can. So I've kind of created my own nomenclature. By the way, this is the way this is this is set in terms of the chronology. Is if I were to say 1, 2, 3, 4, name these as 1, 2, 3, 4. When I got to 10, that would be seen as 1.0 basically, and it would go back to next to 1. So I always give it a letter and then a number. And so I'm saying thermal 1, SM for small because I'm going to make a larger one at some point. I know what I'm going to do next. I put MF for multifamily. That was the template that we chose. That's not really descriptive, but I'm going to remember since this is a basic thing that I'm doing for this specific purpose. Also, we didn't have a slab. I'll talk about that in a minute, and there's no glazing. I know the direction I'm going here, so I'm saying what we don't have here also. And so let's look at our outputs. First, remember we can switch from IP inch pound to the metric system SI units. System International. I don't know if you've had classes with me. I'm sure I've shown it to you. It's kind of funny. The IP system is the United States, Myanmar, and Liberia, I think, are the only countries that still use it. The rest of the world uses the metric system. So, in a way, I think Climate Studio a little bit begrudgingly includes IP because it's kind of silly. But it is the United States, so we're a pretty big country, and we're still doing it for some reason. So, as professionals in this country, you have to get used to both of them, which is you should get started now because you have to think in both units as best you can. Anyway, so let's talk about what we have here. Site EUI is our first big output, and that refers to energy use intensity. In this case, it's in kilobTUs per square foot. If you're still not clear on these basic metrics, talk to me. We need to go over it, but I'm not going to do it here. Anyway, it's basically just a certain amount of energy used per square foot, and this is a typical metric for because it's per square foot. We can compare sort of apples to apples. We can compare buildings of the same categories to each other because we'll learn later about we'll talk a little bit later about how larger and smaller buildings, why they have different sort of levels of performance or ways they perform. So anyway, that's our first thing, site EUI, and we get a number per square foot, kilobTUs per square foot. If we go to SI, it's kilowatt hours per meter squared. Kind of makes more sense. Kilowatt hours, something that you're probably familiar with in terms of energy. The next metric is operational carbon. This is awesome that it's here because we need this for Local Law 97 compliance, and so we will use this extensively. However, in this is kind of what I was saying with the IP units. In Climate Studio, this is wrong in IP units. It's just completely crazy off. I've contacted them. They say that they're going to update it in the next, and I have a few other things I found like that. By the way, Climate Studio is made by an awesome company, SAMELAB, which is a spin-off from an MIT research project. They make this available to us for free to anybody in education. It's just an awesome thing they're doing, and so anything we can do to help them, let's do it. And I definitely, so if you find any problems, let's let them know. We'll troubleshoot them ourselves as best we can, and then pass them on. Anyway, so if we were in SI units, this works. So it's just something where they didn't convert correctly. And so we can use the SI units, and we'll do a conversion at a later point when we get to that level. But anyway, back to the IP units, which we're used to in the US. So the point is that this is going to be an amount of carbon that's, and it's just basically, it's related directly to the site EUI value. Let's go look at that briefly, because we didn't really do that before as an input. Just edit one. Oh wait, I know I'll do. Let me go to the. I'm going to edit my zone. If we go to settings, that's where the cost, both in carbon and dollars, is. These values here are, so you have heating, carbon, and again, this I think should be pounds per kilobtu, not kilograms. But anyway, well, don't worry about these. We'll do a separate spreadsheet on this when we need to use them for our purposes. But the point is that we have heating CO2 in BTUs per year. We have cooling CO2. We have hot water CO2, and we have electricity CO2, because these are going to be different systems that are going to be creating those loads, and so, or using that energy, and so they may have different sources, and so this is where we can determine the carbon emission footprint of the different mechanical systems that we're using. So that's why, that's where this comes from, and it gets added up and brought here as a single number that we'll use. We can also get an energy cost. This is just in per dollar. So our energy here is somewhere between $1 and $2 per square foot. Then there's a percent save. What is that? That's based on this baseline number. The baseline number comes from a big database that the U.S. government has created. We'll talk about that maybe at some point. Or any of these things that people are curious about, talk to me separately. We can go into more detail. But basically the point is that there's a database of buildings. This is an average or a mean for buildings of this type. So we chose a template that was a multifamily apartment building. So this 49 baseline EUI is just saying, well, the average building like this in the U.S. would use 49 kilobtus per square foot per year. So we're already a little bit below that because of the presets that we chose. To get to local law 97 compliance, we have to get way below the baselines. So that's not very impressive at this point. Okay, so then we have building and zone summaries of this data, which are really, really helpful, and we should spend some time studying them. I'm just going to be brief here, but there's a huge amount of information here that you can use as you're developing your projects. You'll see how quickly you can get this information, and you can use it as a way to troubleshoot or just think about design decisions you're making. I'm not saying that your energy use should slavishly control your form, but it's really important that they take shape together, form and performance. So, and this is a way to do it. Okay, so we have then our energy use intensity per square foot in graph form, separated by month, and we have it broken up into different the percentages of different building components, or for example, equipment, fans, that's going to be ventilation, light, so lights, hot water, heat, and cool, and so we can get some quick information right away from this. We can see that we have pretty big lighting load. Lighting power density would have to be knocked down, or maybe we can add some. We have no windows in this building, so we might add some windows and be able to have more daylighting, and therefore maybe lower our lighting power density. We have a heating load and a cooling load. Heating is red in the winter, cooling in the summer. It's interesting that June and September are the same size and pretty small. And then July jumps up and August starts going back down. We could think about why by looking at the climate data, but this would also, we might be thinking about how we're going to situate our building or tweak it or adding shading or whatever it would be. At this point, we're just got a box with no windows, so that's not what we'd be thinking, but just saying that there's a lot of information here and it's graphically very clear. The second drop down is also EUI. It's just straight up, it's total rather than per square foot. So it's just exact same information, but totals, which can be helpful for other reasons. But it'll always have the same shape because it's the same information. Then we have zone temperature curves. Actually, let's go to energy flows next. This is an incredibly helpful graph for iterative design. We have again, so on the left, we have kilobtus, and there's a black line in the middle, which is 0. And so everything above it is gains, and everything below it is losses. And the gains and losses have to even out because we have to get to where we have. Well, let's put it this way. In the winter here in January, we have this many losses. What are they from? So the darker blue is from mechanical ventilation. That means we have mechanical ventilation turned on in our template, and so we're bringing in outdoor air. And even though I think we had energy recovery ventilation turned on, we're losing some energy in that process. We're losing a fair amount in infiltration. So we might be able to tighten up the building. But anyway, we're losing there, and we're losing a fair amount through the envelope. So that's the green. And then we got some gains. We've got the equipment is putting off heat in the winter, which is helpful to us. People are putting off. The red is just people. That's from them metabolizing food, and that we get to use this heat in the building. Some buildings get so energy efficient that this is really a huge part of the heating load. And then lighting here we can see is a large portion of the load. But you think about it. So in the winter we're going to need, our losses are more than these gains, and so we have to make the rest of the losses up with something that this light gray color, which I made a little darker, is what our mechanical system is doing to replace the heat that's being lost. And so you'll see that then there's always, if there's a month where there's a real parity between losses and gains, so this month here in May is passively ideal, and we have no heating or cooling load, or if we do, it's tiny. But most months, so like in July here, we have many more gains than losses, and so we're having a cooling load here, which is what this gray is. And so we can come in and study these months and decide and learn things from it. Like, well, what do we want? Low-hanging fruit here would probably be to try to see if we can get our lighting better. Maybe we want to try to improve the air tightness if that's something that's or just check the setting. But then we also thinking in terms of, well, like air tightness is actually construction. So if we've already built the building, for example, that's going to be difficult, or it's going to cost a lot of money to change that. Whereas lighting is something that we can change more easily. But if we haven't built it yet, air tightness can be something that we can pretty easily fix or improve in many situations, and so we might want to focus on that. So that's what we're looking at here, and the information we're getting to help us in our design. And again, this is just a box, right? So we can do this very early in the process. And then zone temperature curves. This is about comfort, and this is a really cool feature that they've added. What we have here is the gray is essentially the comfort zone. Like from the psychometric chart, and there's some variations on how that's defined. Doesn't matter, we're just playing around here. And then the blue and red lines are the temperature throughout the year in terms in numbers of hours. And so what this is saying to us is that we don't have very many hours. Actually, looks like we have 78 hours that are below outside of the comfort zone and lower temperature. I don't think we have any that are above the comfort zone in terms of being too hot. So so the point is here that really, I mean, we're trying to save energy and money, and we got to be dealing with climate change, but we're also talking about making a comfortable building, so we have to always be thinking about comfort. I need to bring up another term here, building science term, operative temperature. This is not dry bulb temperature. It's not the air temperature. This is a more nuanced comfort metric that takes into consideration mean radiant temperature, dry bulb temperature, and airspeed. But at a fairly low airspeed, it just equals the air temperature divided by the mean radiant temperature. And if you don't understand that, we can talk about it. But mean radiant temperature. Let's take an example. Let's say you're sitting in a room and you feel cold. It's winter. You feel cold. But you look at the thermostat and it says it's 78 degrees or 72 degrees or whatever it's set at. And you get a thermometer out and it actually says that. And you're like, well, I thought there was something wrong with the HVAC system, but it's actually doing what it's supposed to do. Why am I cold? Well, it might be because there is a cold window next to you or a wall that's to the outside that's not well insulated, and its mean radiant temperature is low. And so then your body is radiating heat toward it, and so you feel cold. So we can't just design for air temperature, or we'll get into these, we'll have difficult situations like just described. So we need to have a more nuanced approach, and this simulation is letting us do that. Anyway, enough said on that right now, but we can talk about it more. And then, okay, so that's what we have for the full building, and then we also have a version of this for individual zones. So if we had multiple zones, this would be much more complicated. In our case, it's just a single zone, but let's look at it just to get an idea of what's going on here. So we have the full year down here with this sliding, with this slider, so we can choose small numbers of days. And then we have our chart here that is showing operative temperature, which I just described, air temperature, mean radiant temperature, and relative humidity. So let's see if we can understand. Remember, this is our model right now is just a box with no windows. And so it is going to be pretty straightforward. There's not going to be any air movement, and we're going to have, so the air temperature is this brown line. The mean radiant temperature is this orangish line, and the operative temperature, which would be the average, air temperature divided by mean radiant temperature. So the average of those two, or the mean, is this, which is the operative temperature. And then we see humidity, which is kind of going all over the place. I think we didn't have humidity control in our model, so that's maybe why. And we can compare summer to winter. One thing, since we don't have windows or anything, it's going to be a pretty consistent flow of relative humidity. Why is our relative humidity lower here in the winter in the summer than here in the winter? It's because the same amount of humidity in the air will be a lower relative humidity in the summer because of how relative humidity works. We can talk about that. Okay, but the point here is simply that this is a very useful tool to dial in on zone-specific problems that we might, or just curiosities or design issues that we're thinking about. And then we also have an energy flow for the same. We're not going to learn much about this until we have some windows or other things going on here. So I'm just not even going to talk about it until we have a comparison. But realize it's here. It's just like this energy flow, but it's for individual zones, and so it's a little more granular. Okay, so that's basically what we have for thermal outputs. So we have a ton of inputs, not as many outputs. all right, who cares? Why is this helpful to us? Hopefully it's already obvious why it's helpful, but let's make a few changes and see if we can make some comparisons to quickly just get an idea of what we might be doing with this. But again, what I'm trying to do is just get you started looking at understanding the inputs and outputs. But let's make a couple of changes. So one thing I did not do was I didn't add this slab. So right now, let's talk about how this works. Remember that we had our, I don't know if I ever actually talked about that here. You know, we're basically, our interior space is surrounded by this volume of exterior climate, right? And that I'm representing with this sphere. And so that means that all of these surfaces are open to the air, right? And if we don't say anything else, then the assumption by the model is that everything is open to the air. But that's not true, right? We're sitting, in this case, you know, we're sitting on the ground. Our slab is sitting on the, or our floor is sitting on the ground. It's a slab on grade, and so. Sorry, my mouse is glitching out a little bit. Let me turn back. So we need to identify the ground, the grade slab. So let's do that. I'm going to come and select my my slab layer and make that a. So I'm over here. So what do we have over here? We have zones, exterior windows, interior windows, shading, ground, which I'm going to add, and then add an adiabatic boundary, which I will talk about in a different video. So don't even worry about that right now. Except to realize this is a way that you can isolate. If let's say if our building was we had a space next to it that we were not considering right now, but it was an interior space, and we wanted to assume that, for example, one of these walls, like this wall here, was not going to lose any heat or not have any heat transfer either way. That would be called an adiabatic surface, and we would have to identify that. So it's just say don't deal with that surface, don't have heat moving through there. But we're not doing that right now. We're going to put the slab on the ground. So I'm just selecting the slab, and there it created a ground boundary. We can see that it is this slab. There we go. Didn't want to select. But anyway, that's we've identified the ground. So let's just run the model and see if that changes anything. Again, just there's this window opens up, a DOS window to run the model, and here we are. So this was the model we did before without the slab, and here's the one with the slab. And let's look at our UI. There's actually a pretty big difference. I'm going to go ahead, by the way, I'm just going to, this is the same, I ran this separately and I've named it small, T2 small multifamily slab. You can see it's the same data between these two. So I'm just going to delete this. To delete, you just come up to the X as per typical. Say you don't want it, get rid of it. Okay, so let's compare these two runs and see if we can figure out what's going on. Why would we have a lower EUI with the slab? Well, our common sense answer is that you think about it. So if we're in New York, this air around the building is going to have a pretty, so inside the building, let's say we want to be 70 degrees Fahrenheit. Throughout the year, the temperature outside is going to go well above and below 70 degrees Fahrenheit. So that's going to cause a lot of heat loss and gain, both to our detriment in terms of having to maintain our temperature. But the ground is at a much more stable temperature. Like now, like 4 or so feet below the ground, it's probably at 60 degrees or 56 degrees or something like that year round. It's going to be a little bit colder in the winter and warmer in the summer at the surface, but there's actually a real delay to that, so it's a little more complicated, and that's all in the climate data. So I think what's happened is just we have a much more stable, it's like almost like it's always 55, it's between 63 and 50 degrees or something like that on this surface, on the slab surface, because it's touching the ground. And so if we look, let's see if that makes any sense. So I'm without the slab, I've got no losses in the summer through my envelope, and therefore I've got a pretty big cooling, or as part of this picture, I've got a pretty big cooling load here, right? And if I look at the slab, now I've got a bunch of losses through the envelope and no cooling load. Well, losses are bad, right? No, they're not. If it's the summer and it's too hot inside and the floor becomes a heat sink to pull heat out of my slab, especially like at night when, well, anyway, let's not get into details. Just say that if you imagine this is 50 degrees, 55 degrees, and the slab is touching the ground and the air inside's heating up during the day, or there's we're having to keep it at a temperature that's higher than the outside air. It's going to be more efficient. It's going to have less heat moving through the slab, and so I think that's going to lower our heat load, which seems to be what's happening here. If we look at, the winter is pretty similar, so we're getting the same losses. So there's this would be a more nuanced thing to consider, but I think that's one of the main things that we've. This is one way that you can use a model. You can have some concept from building science of what you think is going to happen, run something and see if it makes sense, and if it does, then you can say, okay, I can understand how to deal with this in my design. For example, I might not want to insulate under my slab in New York. I don't know. That's something I would play with. There's already a code about it, but I mean, it's something to try, and this was an initial foray into seeing what that would mean. We can also see the differences in a bunch of other things. We have a cooling load here, like I said, in our energy use intensity. Without the slab, with the slab, the cooling load's gone for the reasons that I think for the reasons I said. There's a little bit more of a heating load, which will probably be related to those losses, but they're much less, so that the overall effect is to have a big drop in the EUI. All right, so just by making that one change, we learned a lot, right? And we also learned that we can't forget that surface in our model. So a lot of, if you know any engineers, engineering is, you have to be pretty organized and careful, and that's something you really have to be when we're modeling these things. So we're doing our architectural design, we're being creative and, pushing the envelope there. And we just need to, periodically or fairly often stop and say, okay, what do I want to model? What do I want to keep track of in terms of a model right now? And go through the steps and just carefully catalog it so that we have that information in a clear form as we move forward. And then if you do those two things together, you'll be in good shape, I think. Okay, so let's now do one more thing. Let's add windows, because right now this isn't really a building of any kind that you would ever build. I'm going to, I've already created some windows, and let's actually look at these. If I'm going to select, oops, what did I just do? I'm going to select this surface and see what its area is. So area is 200 square feet. And then I'm going to select this window. Let me do it here. And area 96 feet. So if we already know basically what that is. It's about 50%, right? But let's just go ahead and do it. 96 divided by 200. about 50% glass. That's actually a lot more glass than code allows. Something else to talk about. But anyway, so we have a 50% window to wall ratio is what that's called, and that's a term you're going to hear. So just good information to have. So I've got these windows. I'm going to now select them, and I'm going to add them as windows. So here, add windows. I'm just going to leave the default glazing, which is a single pane glass with a high solar heat gain coefficient. We'll talk about glazing in another video. So now I can run my model with, so I've got a slab, I've got my walls, or my envelope, my walls, and I have windows. And by the way, these windows are placed, it knows that the model knows where to put them and on what facade to put them. And so when we get more complicated, we can actually name these faces, or these, we can name our zones, and we can clearly keep track of where our windows are, because we may want to change different, we may want to have different glass on different faces. Anyway, so now we're ready to run the model. And I already ran it, so let's just show you that these are the same. So I'm going to delete that, just so, because I've already named the other one. And so it's a small with the same multifamily with glazing default. I didn't put slabbing because I figured I'll know it because I had it before and I didn't change it. Just whatever nomenclature makes sense to you. But let's see then. So now we're at 74 EUI, whereas before with the slab we were at 39. Huge change. So adding that glass caused us to use a lot more energy. So let's see if we can look at why. So obviously, first of all, let's go between these two. We now have we have a cooling load again. We have a much higher heating load. I'm just clicking back and forth, but also realize that the y-axis will change in its range. So sometimes the shape will look the same, but it's drastically different. So with the glass in the winter, we're using, in the month of January, 12 kilobTUs per square foot, and without the windows, we're only using, actually it wasn't 12, sorry. We're at 12 total, but we're going from about 2 to 12, so about 10 kilobTUs per square foot. And without the windows, we were using about 2, maybe 3. So huge difference in January. There'll be a lot of different ways to analyze this. Let's look at the energy flows. Of course, we have glass. Well, there you go. There's our glass in the orange. It's a little bit unfortunate. I think they use the same colors in the energy use intensity graph. The orange is hot water, and in the zone temperature, in the energy flows, it's glass. But we can see, we obviously had no glass in this one, so the glass has created huge problems essentially for us. We've got a lot of overheating in the summer from the glass. We have some gains in the winter, which is good, but we have a lot more losses in the winter than we have gains from our glass. So adding this much glass of this type is a real bad decision for this model, but for our comparisons, it's actually really good because we can learn a lot. Another thing is we go to the zone temperature curves, we see that we've in the winter we're dropping way out. Let's see, we have outside of comfort zone, we're 2,400 hours outside of the comfort zone, and we're below 60 degrees 206 hours. How is that possible if we have HVAC on? Well, for one reason, if we have a mechanical system, for one reason, because of things I said, the mechanical system's set for 70 degrees, but the window surface is going to be 30 degrees if it's 20 degrees outside. So we're going to have a really bad mean radiant temperature balance for comfort. And there are other reasons. So it's really good to check the comfort when you're doing these things too. So this is clearly a bad idea, but I knew it would be. Single pane glass is not legal anymore that I know of, but we still have it in Ed Hall. That's all single pane glass, and I'm not sure. I think there's some single pane glass in in our building in Manhattan. off of Columbus Circle. So it's around a lot still. And then if we look at our, this is where these charts are pretty interesting. If we look at the temperature here, we can see, let's see, a lot more fluctuations. And if you notice, like to say in July, actually let's just, cause I don't want to spend a lot of time on this. Let's go to energy flows. We can see that in the winter, we're getting a lot of gain. I mean, a lot of, let's see, the windows are, hold on a second. So you'll see that in the winter, so this is the windows here. We have let's say in January, we have some good gains in during the day, but at night we have fairly large losses, and so we are getting some gain, but you know, at certain times we're getting more gain than loss. But you know, this is stretched out over a longer period, so I bet that's the same amount. You know, and we could analyze this more closely. But then if we go into the summer, we see that we're getting huge gains, and we don't want them because we're trying to cool, and then very little losses at night. So it's a big bust in terms of heat balance for windows in this configuration. We also then, if we go to temperatures, we can just see that the windows have introduced a huge, because this is another thing we should remember to do always, is compare these. So, you know, if I'm looking at just a slab without windows, this is very stable, right? And then if I bring in the windows, I get all this variation from it. Again, very straightforward and obvious, but it's cool to see that it actually works. Same thing if we go to temperature. The main things the windows are doing is just they're adding a huge amount of variety to the temperature profile, which is hard to control. Then if we go and if we look at daylighting, there's going to be a lot of glare issues. So in a building this size, this many windows are really hard to deal with in single pane, which is what every house had, you know, in the 60s, or well, until much more recently than that. Of course, I'm talking about the 1960s. Anyway, okay, so that's all I wanted to do on the outputs. So we've talked about inputs and outputs. We have a good handle or a good introduction to the very basic layout of the thermal analysis or thermal simulation in Climate Studio. So next, let's use it for some interesting, to see what we can learn about simple changes in buildings moving forward toward something you can use in your studio projects.